Good morning. In the fourth module, we have learned about entropy, the Clausius inequality and equality, the change in entropy, and change in entropy for reversible processes and different irreversible processes, etc. So the second session of the fourth module is thermodynamic potentials. That we can start today. Thermodynamic potentials. So you have heard about the potential. Already you have learned one of the thermodynamic potential. Thermodynamic potential is a state function. That as in mechanics you have potential. You learned about the potential V. So here also we have different potentials. Thermodynamics you have different potentials. One is the internal energy. What is the peculiarity of a potential? A potential is actually a state function. It never depends on the intermediate path. So you have learned the changing internal energy, some UF minus UI. That difference is depending on the adiabatic work. If the process is adiabatic, something like that you have learned. And the first law, we have derived the first law, and the differential form of first law you have already derived. That is the case of internal energy. So these are fundamental functions. Thermodynamic potentials are fundamental functions and that are used to describe a state of a system. Of course, the state of a system can be represented by equation of state, and together with that equation of state is depending on thermodynamic variables. You have the equation of state PV equal to nRT, etc. like equations you have learned. And together with that also PV, etc. are also potentials, or it depends on the state of the system. So these thermodynamic potentials, these four potentials are there. These thermodynamic potentials together with the state of this system can describe the complete properties, almost complete properties of the state of the system, or the properties of the system in an equilibrium condition. So we cannot use non-equilibrium state, or we cannot use the state of the system or equation of states for non-equilibrium systems. So we need equilibrium. The system should be in equilibrium. So we can use the equation of states, the thermodynamic potentials, etc. So it actually gives internal energies and energy, So these thermodynamic potentials actually give the energy of the system in different ways or in different conditions. It will give the energy of a particular system. So we can start with this, and also these potentials are functions of different thermodynamic variables. So internal energy can be a function of one or two variables. These other potentials are also functions of thermodynamic variables, etc. So there are four thermodynamic potentials. The first one is you have learned, that is the internal energy. Represented by the letter U. This is the first one. And the second one is enthalpy. Enthalpy. Represented by the letter H. Third one is Helmholtz free energy. Helmholtz energy, represented by K. And the fourth one is Gibbs free energy, or Gibbs energy, represented by G. And these are the four potentials actually we can use in thermodynamics. These are the four thermodynamic potentials. And we can derive the equation, or we can give some connection between these potentials and thermodynamic variables. potentials, and you also have differential form of these equations or these energy functions or these potentials. So we can start with internal energy. That properties already you have learned. Anyway, you can just start with the properties, some one or two things or one or two equations with the internal energy. So we can start with that. So the first law actually gives the change in internal energy. These are the two states, final state and initial states. In between states we are not considering. If it is non-equilibrium, there may be non-equilibrium states in between this UF and UY, that we are not mentioning. We are only considering the equilibrium state, some initial equilibrium state UY and some final equilibrium state UF. So this we have an equation, that is Q plus W, and this Q, for this equation this W may be diagonal. For adiabatic process, UF minus UY is W adiabatic. That you have already learned in the first law, that second module. You have already learned. So this is the general equation for the change in internal energy, and also you learn the differential form of this internal energy, that is dU is equal to d bar Q plus d bar W. We can just rewrite the equation. What is dQ in terms of change in entropy? That is dQ by T is actually ds, the change in entropy. So T into ds may be dQ. So we can rewrite the equation as T ds plus dW. What is d bar W? That is actually minus PdV. So we can write dds minus PD. That is dU is equal to TdS minus PD. So from this is the change in entropy and this is the change in volume. So we can write here as U is a function of V and S. We can write U is a function of V and S because this is ds and this is dV. So this directly representing U is a function of, you can be represented in terms of change in volume and change in entropy. That is the meaning of this equation. You can represent U in terms of change in volume and change in entropy. So we can use this equation. We can use the internal energy, this dU equal to TdS minus PdV equations for problems which are connecting, or there may be change in entropy and change in volume. If there is a problem having change in entropy and change in volume, you can use this equation for solving the problem and find the state of the system or the properties of the system. You can use this equation. So this is the first one. We are not going deep into it because we have already learned so many properties of this internal energy, etc. So this is the equation, that is UF minus UY equal to Q plus W, and dU is equal to dQ plus d bar Q plus d bar W, and dU is equal to TdS minus PdV, and then you can write U is connecting the two variables V and S. So the second one is enthalpy. The second one is enthalpy, represented by H. So you have the equation for enthalpy H is equal to U plus P. This is the relation for this enthalpy, which is connecting the internal energy, one of the potential or one of the potential function, and P and V. So if you are taking the change in enthalpy, that is dH, which is equal to dU plus dV plus ddt. Then what is dU? dU is equal to TdS minus PdV plus PdV plus dV, which is cancel. So this will be TdS plus V. That is dH. Or we can write H is a function of S or P and S. H is a function of P and S. You can write from this equation. And this enthalpy change, this equation can be actually used for solving the problems containing heat capacities, heat capacities and heat of reaction, latent heat, in which pressure is one of the variable. Pressure is determining the state of the system, because this is changing the pressure change is there. So if there is a state or there is a process in which pressure is changing, then for solving the problem which is relating or which is connecting heat capacities or heat of reaction or latent heat, etc., you can use this equation. That properties we can learn later also, the properties of the enthalpy deeply, how it comes, the latent heat, etc. we can learn. So just you understand now that this equation can be used for solving problems which is in which heat capacities, latent heat, etc. are the variables or are coming into it. Or we have to use such properties, or we have to use such quantities, heat capacity, heat of reaction, etc. If pressure is a variable, then you can use this equation to solve the problems of such systems. So the third one is Helmholtz free energy. Helmholtz energy represented by A. So Helmholtz energy or Helmholtz function represented by A, and it is represented by A is equal to U minus T. So the small change can be written as dA, which is equal to du minus TdS minus SdT. Then du is equal to TdS minus TdV minus TdS minus SdT. So which is equal to TdS will get cancelled. So we will get minus TdV minus SD. So immediately we can write A as A is a function of V and T. So this equation, this Helmholtz function or Helmholtz energy equation can be used for processes. There may be change in volume and temperature. So we can use this equation. This is the Helmholtz function or Helmholtz energy A, which is equal to U minus Ts, and dA is equal to minus PdV minus SdT, and then you can write A, which is a change in variable which depends on the change in volume and change in temperature, or function of V and T. You can immediately write. So the fourth thermodynamic potential, fourth potential is the Gibbs free energy. Gibbs energy or Gibbs function. Gibbs function or Gibbs energy, both you can say, represented by G. And this G can be written as H minus T's. Then immediately you can write the change. dG is equal to dH minus TdS minus SdT. Then what is dH? dH is equal to TdS plus dVP minus TdS minus SdT. So again this TdS will get cancelled. So you will get VdP minus SdT. function of P and T. So this is the Gibbs function, or Gibbs energy. Actually it is Gibbs function. Then this is G is equal to H minus Ts. So the change dG can be written as VdP minus SdT. Then we can write G as a function of P and T. So these are the four potentials, and this Gibbs function can be used where there is phase transitions, where there is change in pressure and temperature. Or it can also be used where there is phase transitions and chemical reactions. You can use this equation for solving the problems of chemical reactions and phase transitions, etc. Actually, phase transition, the first order, the second order phase transitions are represented by this curve, some change in the dG. It is actually defined in terms of the change in Gibbs function, like that. So this can be used in phase transition problems or heat reaction or chemical reaction problems, etc. You can use these equations, this Gibbs function. So we have four thermodynamic potentials. This change can be written as, we can conclude these four equations. The first equation, the first one is du, which is equal to TdS minus PdV. The second one is dH, the enthalpy change, TdS plus VdP, TdS plus VdP. The third one is Helmholtz free energy, which is minus SdT minus PdV. The fourth one is Gibbs free energy or Gibbs function, which is equal to minus SdT plus VdP, or VdP minus SdT. These are the four thermodynamic potential equations. Internal energy changes, internal energy, change in enthalpy, change in Helmholtz function, change in Gibbs free energy or Gibbs function. These are the four thermodynamic potential equations, and these equations together with the equation of states, different equation of states, can be used to describe a system in equilibrium completely. If the system is in equilibrium, we can use these potential equations together with the equation of states, and which will describe the properties of the system completely, or properties of the process completely, or properties of the system completely. So these are the four equations. So these are the thermodynamic potential functions, and this is having its own importance. And the next section we can go detailed about this enthalpy change, or the property of enthalpy, different properties of enthalpy, how it is connected to latent heat, etc. And then the different properties of this Helmholtz function, different properties of this Gibbs function, etc. The internal energy we have already learned in the second module. So you can use one or two things from here. This internal energy, you can just write one equation more. That is, you can write this equation as U as S and V, function of S and V. Then we can write du is equal to, in the partial mode, dou U by dou S at constant volume into ds plus dou U by dou V at constant entropy into d. So we have the two equations. One is du is equal to TdS minus PdV, and the other one is du is equal to dou U by dou S at V into ds plus dou U by dou V at S into d. So comparing these two equations, this is ds is here, ds is here, dv is here, dv is here. So comparing these two equations, you can write dou U by dou S at constant volume is equal to T, and dou U by dou more complicated one. So we will get such a property that dou U by dou S, changing this internal energy with respect to entropy at constant volume, is actually the temperature of the system, and also changing entropy with respect to change in volume and constant entropy will actually the pressure minus of the pressure at a particular time at that system. So you can directly use, if you need to integrate such equations, you can directly replace this quantity by T and this quantity by minus V. Then the integration will be more easy. So these thermodynamic potentials actually all are in changing. All equations we are representing in change or differential equations we are using. Or we can derive the properties of the system by differentiating the different potentials. That is, there is a very large meaning, or there is a meaning if we are differentiating these equations. So the thermodynamic properties, all the thermodynamic processes or the thermodynamic properties of systems can be calculated by differentiating the thermodynamic potentials. So this is one differential form of the equation for internal energy. Like that you got three more equations, that is for internal energy change, Gibbs free energy and Helmholtz function, etc. You got different differential equations, and these together with the equation of state can be used to find the properties of the particular system. So next you can study very deep into we can go deep into the enthalpy of the system, that we can take in the next class. Now we can stop. Thank you.